Let's come back to our class. So basically in the last class, we have been talking about applications of the max flow algorithms. So basically the first problem that we actually take a look is the bipartite matching problem. So basically we basically prove that for the bipartite matching problem, so you can actually actually have a vertex S on the left-hand side and actually another vertex T on the right-hand side. And basically, you direct all the edges, from original L to R with the direction from L to R. And then basically, you have this vertex S and T here. And basically, you can construct all the edges from S to all of the L and construct the edges from all of the R to T here. So basically, we just proved that the maximum cardinality of the bipartite matching is actually equal to the value of the max flow in this new graph here. So a last note that we can actually do is that we just need to consider like the cost. So cost actually, we actually have two bounds, O of MC, which is the original Ford Fulkerson algorithm we proved in class. And actually another bound that we mentioned is O of M squared log C here. So it actually becomes very important. What is the value of C here? So actually the C here is actually at most N here because you just consider the S. The S here, you have all the edges to all the vertices here. But actually, the vertices on the left-hand side and right-hand side, they should actually just equal to n of half each. Or maybe you can just feel free to take a half here, but that is not so important. But actually, in any case, the C here is actually smaller than or equal to N here. So basically, we see that in this case, the complexity of the original for the Fulkerson algorithm is O of Mn. But actually, on the other hand, if we use this trick of consider the scaling here, the complexity here is actually M squared log N here. But actually, M squared log N is actually equal to M times M log N. It's actually in general larger than Mn. Because typically for the matching problem, the number of edges can be as large as N squared. You could just consider all the edges between the left part and the right. So there are going to be N squared edges. So in general, actually, M is actually larger than N here. So needless to say that M log N is typically larger than N here. So in this case, actually, further algorithm is not so helpful. So typically for a lot of applications, we know that the capacity C here is actually at the most N here. And the surfaces that we just ran for the Fulkerson algorithm, and actually for this problem, we have a complexity of O of Mn for solving the bipartite matching. Okay, so this is like a last node for the bipartite matching problem. And basically this finishes what we want to discuss here. So is there any question about the correctness and actually the running time of the max flow algorithm for solving the bipartite matching? Okay, so if there is no question, let's continue to talk about some further examples of using the network flow algorithms. So the next example that we want to talk about is called a disjoint path. So this is actually another a graph problem, but finally we will see that actually the network flow algorithm can also be applied to some maybe some problems also out of the graphs. But let's see see an example of the disjoint path is. So basically here we say that we are actually given a directed graph. G with a vertex at V edge at E here, and actually two nodes S and T. So we actually want to find the max number of edge disjoint ST path is. So here G path is edge disjoint if they have no edge in common. So here it's basically a problem that we want to consider the number of all the possible edge disjointed paths here. So here we make a quick assumption that actually without loss of generality, we can actually assume that S only has out edges and T only has in edges. I mean, here we are talking about, paths, from S to T, ST paths here. So it is possible, there are some edges, basically there are some out edges from S. Sorry, some in edges at S, and actually also some out edges at T that constitutes in part of the ST paths. But actually for ST paths, like this, maybe you have an S here, and actually S has some in edges, and maybe you have like a T here. The T has some out edges here. So it can only be the case that you actually do something like this. And maybe for instance, you have like a path like this. So this is not something we are so interested, and basically in such kind of case, basically we just remove such cycles. So that is the reason that, in general, without loss of generality, and for the interesting cases, we just feel free to ask to assume that actually S only has out edges and T only has in edges here. So such kind of problem, basically the disjoint paths problem, it actually also has wide applications in general. So for instance, maybe we can consider like a communication network. So for a communication network, basically, maybe for instance, let's assume that we want to consider the way that maybe for instance the S here, it can only communicate to one and can communicate to two, and maybe can also talk to three here, and maybe have some other vertices. So 4, 5, 6 here, and maybe finally a T here. So let me actually draw some of the edges here. So in the middle here, the direction of the address can be a little bit arbitrary. So maybe for instance, is something like this. So let's maybe for instance, take a look at this. So what is the number of edge disjointed paths in this graph? So we can actually find an example that actually, let's, oh, this is not what I want here. So let's copy this and paste it here. So for instance, we can find out a way that actually this graph has a two edge disjoint paths. So for the right colors, this is one of the ST paths that we can consider this. So this is one of the edge disjointed paths. And we can just use another color to represent another edge disjoint path. So we use the blue here, we use the blue here, we use the blue here, and actually the blue here. Okay. So basically for this problem, the number of edge disjointed paths is 2. Okay, any question about the edge disjoint problem, basically its definition? So as we are talking about the max flow, the applications of the max flow algorithm, it's definitely the case that next we are going to give a max flow formulation for the problem. So the thing that we are going to do is actually quite similar to what we are actually doing for the bipartite matching case. So basically we assign a unit capacity to each edge. And actually the thing that we are going to prove here is that the max number of edge disjoint paths equals to the value of the mixed flow. So that's actually a rather sound formula. So the max number of edge disjointed paths equals to the max flow value. So this is something that we are going to prove here. So actually, similar to the proof style for the bipartite matching case, we are actually also going to have the smaller than or equal to part and actually the larger than or equal to part. So for the smaller than or equal to part, I mean, this we just do this. So suppose there are k edge disjointed paths. I mean, let's say there are P1, P2, and 2 Pk here. And then as surface as we said, actually, F equals to 1 if E participates in some path Pi. Else, let's just set F equals to 0. So since the paths are edge disjoint, so this is basically something we can directly utilize. I mean, in the formulation of the network flow here. So we know that since edges are edge disjoint, basically F is actually a flow of value K. I mean, we have a valid flow here that only is going to say that the max flow as value at least K here. So basically, this is the smaller than or equal to. So the remaining thing that we are going to prove is the larger than or equal to part. That is basically the max number of active disjointed paths is larger than or equal to the max flow value here. So here, basically, similar to the proof that we use for the the bipartite matching case. Basically, suppose the max flow value is K. Okay. So still, the next thing that we are going to use is going to use the integrality theorem. So using the integrality theorem, we know that actually K is an integer. And actually there is this 0, 1 flow of value K. So because still we assume that the capacities of all the edges can only be a 0 or 1, and we know that it's actually integers. So we just know that this is actually going to be a 0, 1 flow. So the thing that we are going to do is that, I mean, there actually are some edges, I mean, in this flow that actually have the corresponding function value to be 1 here. So we just consider the edge. I mean, let's say we say from S here. So we just consider edge SU with function value FSU equals to 1. So basically, we know that actually by conservation, so by conservation, there actually exists edge UV with FUV equals to 1. Because actually we have an S, we have a U, and we have such kind of edge, I mean, with the corresponding with 1. So we know that we have the conservation requirement, and U is basically not S and T here. It definitely is going to have an odd edge 1 here. And basically, this is the vertex on V that we actually concerned. So maybe let me actually move this here to basically represent what I'm actually saying here. So, I mean, from S to U here, we then know that there is actually another edge, I mean, U to V with the corresponding value of UV equals to 1. But actually, there are some further areas, and we can just continue this. So we just say we continue this. And this actually must finally reach T. So this is basically because all nodes in the middle as conservation. And actually, we know that actually we without loss of generality, we have already removed the cycles at SNT, so it cannot reach S. And they're actually at most M steps. So I mean, as long as you're U and V or whatever in the middle, I mean, we just do this. We just do this routing of the edges continuously. So basically, we move from S to U, and we know there are actually another edge. I mean, from U to somewhere else that's called V with the corresponding value of FUV equals to 1. We just do this again and again. But actually, there are just finite number of edges, and this thing must stop. And basically, do this when it stops. It basically reaches S or T here, but we have actually removed all the cycles at S and T here. So we know that definitely we actually are reaching a T here. So basically cannot reach S, and there are actually most steps. So basically C, we reach T. So what we do then is that basically we just remove. I mean, basically we doing this. We reach from S to U, from U to V, and finally we reach T here. So basically this gives you a path, and we just remove such a path. And this actually gives a 0, 1 flow of value k minus 1. So what we do here is that in some sense that we're doing the above procedure. For k times. And we just going to produce k edge disjointed paths. And basically, we have assumed that the max flow value is going to be k here, but actually in this graph, we have already constructed, I mean, k edge disjoint paths. There might be the chance that there are more edge disjoint paths, but basically we are proving the greater than or equal to sign, and this basically finishes our proof. So similar to the case we were talking about the bipartite matching, I guess we can also talk about the running time. The running time is that still we know that each edge actually has capacity at most 1 here, and actually we know that C is going to be at most n, because actually there are at most n vertices. Actually, I mean, only considering the odd edges from S here, they're actually at most m edges. Sorry, at most n edges, and each of them has capacity 1 here. So we definitely know that C is actually smaller than or equal to n here, equals to O of n here. So this is actually giving that the overall cost is O of n for solving the edge disjoint problem. Okay, so any question about this theorem and the analysis of the running time? So maybe you can probably see that actually for the applications of the max flow algorithms, I mean, actually, I think the proof here is not difficult. I mean, the proof here is relatively straightforward. But what is actually important is that you need to think about, I mean, maybe some problem is not as transparent as the maximum, the maximum number of edge disjoint problem, and also the bipartite matching problem. But actually, you can think about how you want to reduce those to a max flow problem. And then basically, the argument here should not be too complicated, but basically the construction is very important. So let's actually go into a little bit further. Then maybe we want to see a little bit, I mean, some other perspectives of making the construction. I mean, when we want to use the max flow algorithm to solve some practical problems. So here, the third problem that we are going to introduce today is actually called a circulation with demands. So for the circulation with demand problem, in general, I mean, for the max flow algorithm, we have been having the assumption of the conservation that basically the value flow into a vertex and flow out of a vertex. Actually, we assume that they are actually supposed to be always equal here. But maybe in some real application, maybe let's consider, for instance, supply chain, or maybe some other, I mean, some networks that are actually going to happen in the real applications. It may be the case that, I mean, on the nodes, we actually don't have the conservation condition, but nevertheless, maybe we want to have some kind of way to formulate this. So we say that actually here we have a directed graph. So we have a directed graph, G equals to VE here, actually edge capacitors, CE, and actually E is among all the edges. So here we have a way of formulating, I mean, if a vertex is not conserved, I mean, maybe, I mean, overall it has, I mean, a positive flows, or maybe have like negative values of flows. So in general, we call this nodes to be, I mean, call them to be node supply and demands. So what do I actually mean by that? So that is nevertheless a value at each vertex, and let's call it like a D of V here. Actually, V here is taken from the vertex at V. So here we say that if the dV here is larger than or equals to 0, we say this is a demand. And if the value of dV is strictly smaller than 0, let's say this is a supply. So another definition, I mean, after we having considered this kind of, I mean, the vertices with that is actually not conserved. Basically, we formulate as basically the supply or demands of each of the node here. We need to have some further definition to, I mean, this is probably the case. We need to be careful about the existence of such kind of supplies and demands. So that is basically along this, we have some further definitions here. So a definition that we are going to use is actually called a circulation. So we say that a circulation circulation is a function that satisfies two conditions. So basically, for the first condition is that we still need to have capacity on each of the edges. So for each edge E, we actually have the assumption that 0 is smaller than FE is actually smaller than or equal to CE here. So this is basically the capacity constraint. And furthermore, I mean, for each vertex, basically we need to formulate, I mean, what we have for the supply and demands here. So basically we require that a summation of E into V of FE minus the summation of all the E out of VFE. Here, we don't require it to always to be 0, but we require this to be a D of V here. And this is called, I mean, in this new case where we have the supply and demands of this function value dV to not be 0 necessarily, we still have some kind of conservation, but it's conservation under this dV here. So basically, as long as we have this function d here representing the node supply and demand here, we can have this kind of definition of circulation here to characterize the capacity and especially the new constraints for the conservation here. So this is a definition for circulation, and a very natural thing is that we can have a problem called the circulation problem. So for the circulation problems that we are actually given the graph, I mean, given V and E here. And furthermore, we are given the function D and actually the function C here for the capacity on the edges. Does there exist a circulation? So this is called a circulation problem. So among this, I mean, basically we have been talking about, I mean, the supplies and demands of all the vertices. But I guess, I mean, the supply and demand and basically this value, I mean, dV is larger than or equal to 0, dV is strictly smaller than 0. So this is still more like a local property of what we have for each of the vertex. So it's talking about like the demands and supplies, and in general, we have all this kind of summations here. So actually, I mean, we want to be a little bit careful that in general, maybe we have some thing that we must satisfy at the first hand. So this is actually a necessary condition that we want to keep in mind. So a necessary condition that we actually must have is that the sum of supplies must equal to the sum of demands. And actually the summation of all the V dV larger than equals to 0, dV is equal to the minus of the summation of all the V, such that dV is strictly smaller than 0 dV. It must be equal, and let's denote this as a value of capital D. So the proof is actually very simple here. We just take a look at this, and we just take a summation of all the vertices in V here. So we just say we sum conservation constraints for every node V. Okay, so is there any question about the definition of the circulation problem? Okay, so a very important thing is that basically for the circulation problem, we need to determine the existence of circulation that basically given all this capacity bound C and also the function D here to represent the demand or supply of each vertex. We need to determine whether such kind of circulation exists. So basically, I mean, we can clearly see that this is still quite like a max flow problem, but this is not exact. So basically, the key point is that the conservation condition compared to the original max flow problem is actually changed. So basically, we need to have a good way to actually tackle with this kind of thing here. So basically, I mean, we can consider something like this. So we can consider a max flow formulation for this problem that we really want to solve this. Okay, so I mean, similar to a lot of cases, I mean, here it is just like a directed graph. I mean, we have this kind of restriction. I mean, the dV here, and actually also the capacity bound C here. So basically, I mean, to use this, I mean, to basically utilize the max flow formulation for solving such kind of problem, basically we need to, I mean, the first thing that we can just imagine is that we still need to add a source S and a sink T here. The main issue is that the conservation condition is not the same as the max flow condition. And actually, this is a very important point that we want to tackle with. And maybe hopefully, I mean, maybe we want to have a situation that, I mean, we construct a graph such that actually, I mean, we don't have the supply and demands issue, and actually it goes back to the original max flow problem. So to actually achieve this, I mean, a key observation is that maybe we can consider something like this. So basically for each V, each V with a D of V strictly smaller than 0, we actually add an edge from S to V with capacity minus dV. And actually for each V with dV strictly larger than 0, we add an edge from V to T with capacity dV. So this is actually what we do here. So let's see see another example here. So let's see, for instance, this graph. Let's, for instance, see a graph with 6 vertices. So we have an edge with 10 here. We have like a 6 here. So we have a 3 here, 7, 7. And 9. So basically, this is really some, directed graph with some arbitrary weights on the edges here. And basically, the first thing that we need to do is that we want to determine, which vertices actually they have supply and which they have demand here. So we can actually compute the corresponding values here. So for instance, for this vertex, for this vertex, the corresponding value, because actually we are actually having a value 10 out of here, and actually have another value 3 out of here. So we clearly see that basically the value here, and actually I probably made a typo. In general, we can consider some arbitrary edges here, but actually for my preparation, I guess this looks clear. So basically, let's just consider this graph. So basically for this vertex, we have an out edge with weight 10 here. Actually, we have an edge with basically in weight 3 here. So basically, we say that actually here, the dv here just equals to -7. That's actually is out of the weight out of the vertex is 10 here, but only actually the in weight here is actually only 3 here. So here, for instance, at this vertex, so let's take a look at this vertex. What is its corresponding cost here? So basically, basically we can consider the case. For instance, basically the thing. In general, we can consider something that is quite general. We have the in weight here to be 10 here, but actually the out of the weight out of here is actually we have an edge with weight 6 here, and actually another edge with out weight 7 here. But in general, we can also put some arbitrary value dv here. Maybe let's for instance, maybe let's put a dv here to be -8 here. And actually, this recall that this 10 and actually 6, 7 here, there are actually some upper bounds on the weights of the, on the upper bound on the capacity that we actually utilize on all these edges here. So basically, this is something that we can just assign by ourselves. Sorry, I won't say it's probably assigned by ourselves, but we can just take some inputs here. Maybe for instance, if your d here, this input here is actually a -8 here. But actually, it can be something maybe, for instance, like -100. But probably just a -100 is not going to give you a solution for the circulation problem. But maybe assume that we have like a -8 here. Maybe, for instance, we can further assume that we have some the value of the d here. Basically, the supply and demands here can be something quite arbitrary. So let's say that maybe we have like a 10 here. Maybe let's also assume that maybe you have a 0 here, say. So for instance, maybe you have like a -6 here, and actually maybe like a 11 here. So according to our definition here, so basically as long as your d, the value of the d here is smaller than 0, so basically this is the value of the supply here. And also on the other hand, if you have a positive value here, you basically, for instance, like the 11 here, maybe you have like a demand on this. Okay, so this is basically something that we actually want to consider here. So basically we want to consider, for instance, like this graph, for this weighted graph, whether this kind of circulation problem, we have a feasible solution for that. So we can clearly see that basically, for instance, at the very beginning, for this part, this is probably doable. For this -7, you can actually satisfy this. At the very beginning, we can just utilize maybe, for instance, the full capacity of 10 here, at the in capacity 3 here, or maybe for instance, the out capacity 9, and actually the in capacity 2 here, and actually we can make this to be a feasible solution. But in general, maybe if you go to later vertices, this becomes infeasible. Maybe you cannot find a solution for that. So in general, we want to have like a uniform way that we can solve the circulation problem. And basically, this is the construction that we really want to consider here. But in general, the way that we turn this into is that basically for all these d values, it's probably a little bit hard to deal with. But on the other hand, maybe we can turn this to, after having S and T here, we can make this to be a regional McFlow problem by actually having S and T in this kind of sense. So we just let's just like copy this. But we actually add an S here. So we add an S here, and we add a T here. So for each v with the value of dv smaller than 0, we add an edge sv with capacity minus dv here. So this just means that we are going to have this edge. And actually this edge. I think here, let me actually erase these values. And actually we turn all this value on the supply and demands, we turn this into a network flow thing. So here, basically, after having this edge, we add this weight to be 7 here. And actually having this edge, we assign this weight to be 8. And actually having this edge, we assign its corresponding weight to be 6 here. And actually, for the t here, I mean, basically we are good with the 0 here, so we don't need to do anything for the 0 here because it already satisfies the conservation condition for the original max flow algorithm. But actually for the 10 and 11 here, so here we have a weight edge from a corresponding vertex to t here with the weight 10 here, and here we have this weight with 11. So this is basically a construction that we use for the supply and demand problem. And I guess you can just directly imagine that this basically a claim that we are going to give is that the G original graph has a circulation if and only if G prime has a max flow of value D. So, or in other words, I mean, we here have emphasized that the G prime has a max flow of value D here. So the D here is actually the summation, I mean, of all the summation of all the corresponding values with the demands, or the magnus of the summation of all the vertices that with dv smaller than 0, or basically we say all the vertices with supplies. So basically, this is the capital D here. So basically, we want to make sure that this works as long as all these are -7, -8, or 10, -6, 11, they're actually satisfied. And actually, they are satisfied only in the case that in general, maybe we consider such kind of a network flow problem that we have this S and T here, and we just like move all this weight, like all these weights on supply and demands. We turn this into corresponding weights on S and T here. The suffices that the claim that actually we are actually pretty sure is that the graph G has a circulation if and only if the newly constructed graph G prime here actually has a max flow of the value D here. Or we say that this just means that actually it saturates all edges are leaving us entering T. Okay, so this is a direct observation that we can make, and actually I'm probably not going to give the proof here because this just comes very straightforwardly from the correctness of the max flow algorithm. But nevertheless, I think a key thing, I mean, in general, that we have been using a lot in the proof today is the integrality theorem. That actually, if all capacitors, so if all capacitors and demands are integers, and there is this circulation, then there is this one that is integer value. Okay, so any question for this circulation problem? Okay, so this circulation problem, as you can imagine, this is probably some problem maybe you are actually interested in, like a supply chain, maybe in general for some, I mean, real networks. But I guess in general, I mean, this is probably still more like a mathematical model. And I guess speaking of the perspective of like a model here, maybe we want to have like further relaxation along this, and basically want to have a good understanding about what is the power that we can push the limit of the network flow algorithm. Then maybe hopefully there are some other relaxations that we can make. So here we consider, maybe for the rest 10 minutes that we have for this lecture is that for this hour is that basically we can consider furthermore circulation with demands and lower bounds. So what do I mean by and lower bounds here? So that is basically to say maybe we also have some flexibility for the capacity here. And actually, maybe we want to further make some relaxations along that. So let's actually finish this in like a formal sense. So formally speaking, let's actually make this a little bit. So formally speaking, basically, still this is basically just like copying what we have been just saying. So we say that we have a directed graph. G of VE and edge capacities C. And here, what is different is that we have another assumption of the lower bounds of the capacity of all the edges here. So still we are going to have no supply and demands. So still there's a function dv here. Still that if dv is larger than or equals to 0, we call this as a demand. If this dv is smaller than 0, this is a supply. And actually, here, we can still consider this circulation problem, but actually, here the definition is going to be even a little bit restricted. That actually we can consider, a lower bound of the capacity for each edges. So here, in particular, we can the definition that we are currently having is that the definition of a circulation is actually a function that satisfies. Actually, maybe let me remove this here. It satisfies two conditions. So actually for each E in E here, here we can actually further assume that maybe LE is actually smaller than FE, actually smaller than C. And this is the new capacity constraint. And on the other hand, for each B in V here, summation of E into V, FE, minus the summation of E out of V, FE equals to dV. And this is called a conservation constraint. And the new circulation problem that we are actually currently having is then now that we actually are given VE. So note that now we actually have two parameters for the capacity of each edge. So we not only have C here, but actually we have L, C and D here. So we want to ask actually, does there exist a circulation? So this is basically a new circulation problem, but actually right now we not only have demands and supplies, but also on the other hand, we can have lower bounds for the capacity of all the edges here. So basically this is the a new circulation problem that we can actually study here. So here, I guess, the easy thing that we can maybe think about is that maybe, ideally, hopefully adding this L is not too much a heavy burden for us. And maybe we want to, for instance, hopefully we can reduce this problem to the first circulation problem that we just mentioned. And actually there is a way that is not very difficult to do this. So we say that a main idea here is that basically we can model lower bounds with demands. So basically, we can turn all these lower bounds in terms of edge capacities into demands. So what do I mean by that? So for instance, maybe let's assume that we have a vertex V and we have a vertex W here. And maybe, let's say that the direction of the edge is from V to W here. So now, we are going to have some constraints on the capacity here. So let's assume that the capacity here is supposed between like 2 and 9 here. So basically, this is then this 2 is like the lower bound. Originally, the lower bound is always 0, but now we have some non-trivial lower bound, which is 2 here. And actually, we have some upper bound, which is just the C. And furthermore, for the circulation problem, we have like a dV, like a dW here. So the thing here is that maybe we can slightly change the values of the dV, dW, and actually we can somehow make this 2 into this dV and dW. So how can we actually do this? So the thing that we do this is just that we can consider instead a vertex V and a vertex W. We have another edge. We just assume that the capacity of this edge is 7 here. And we just assume that by default, we actually move a value of 2 here along the edge. So basically, if we by default move an edge of the cost 2 along this edge, then basically it just removes the function L here, and the function C here become, after all, here L is a lower bound, and after all, you need to pay this cost. You just move this. In this case, basically the value of the supply and demands are basically the dV and dW here. It's just like the value of the dV here is actually changing by +2. Actually, the value of dW is changed by -2 here. So we can actually make a short conclusion for this. So basically, the idea is just as what I just mentioned is that we can actually model lower bounds with demands here. So the thing that we are actually going to do is that we want to send the LE units of flow. We just send this. As long as this is a lower bound, we after all need to suffer from that. So we just do this. So we send LE units of the flow along this edge E here, and then we actually update. We need to do this. So we need to update the demands of both endpoints. And actually, this just solves the problem. So this is basically suggesting that circulation with demands and lower bounds it's just the same with circulation, just with only demands here. So we can just safely say that we just like let's write this down. So this is just a brief theorem. There is this circulation in G. If and only if there is this circulation in G prime, if all demands positives and lower bounds in G are integers. So basically, we just make a reduction. From this circulation with lower bounds. Just to the case with only. Circulation with demands and lower bounds. So circulation with only demands. And actually, as long as this still basically we have this integrality theorem. And basically, as long as the demands, capacity, and lower bounds in G are integers. So basically, then there is a circulation in G. That is integer value. So actually, a very short proof. This is actually a quite intuitive. I would probably not say it's a proof, but let's say it's a proof sketch. That basically Fe is a circulation. Is a circulation in G if and only if F prime E equals to Fe minus Le is a circulation in G prime. Okay, so is there any question about circulations? I mean, the reduction, I mean, basically the circulation with demand problem, and then the reduction also, if you have the lower bound, this is not a big deal by having this kind of construction. So maybe we can further think a little bit about this, and if you have any questions, maybe feel free to ask me in the last hour of today's lecture. So let's take a 10-minute break now.